In this video, we are going to discuss question based on RL circuit. So let us discuss question 9.49. Consider an RL circuit with resistance R equals 1 mega ohm, inductance L equals 1 Henry, which is powered by 10-volt battery. What is the time constant of the circuit? And B, if switch is closed at time t equals 0, what is the current just after that time? After 2 microsecond and when a long time has passed. So here in this question we have an RL circuit with resistance R as 1 mega ohm. Mega ohm you can write as 1 times 10 to the power 6 ohm. L is 1 Henry and the battery voltage is 10 volt. In part A of the question we need to find what is the time constant tau. Now time constant tau is given as L over R. So we can substitute L as 1. R is 1 times 10 to the power 6. That gives you the time constant as 1 times 10 to the power negative 6 seconds. Or you can write this as 1 microseconds. Then in part B, we need to find if the switch is closed. That means if I close the switch, what will be the current through the circuit at time t equals 0? So this is the first part of part B. What should be the current at time t equals 0? Now the current I is given as I max 1 minus e to the power negative t by tau. This is when the battery is connected to the circuit and the current is increasing. At t equals 0, e to the power negative t by tau will become e to the power 0, which will be 1. So this term over here will reduce to I equals I max 1 minus 1, which is equal to 0. So at time t equals 0, immediately just when you close the switch, the current is also 0. Then in the second part of part B, they want you to find what is the current after 2 microseconds. So now my time t is 2 microseconds, which is 2 times 10 to the power negative 6 seconds. Now we use the same rule. I write I equals I max 1 minus e to the power negative t by tau. That becomes equal to I equals I max. You can write as V over R. 1 minus e to the power negative t by tau. Now let's substitute. I will be equal to V is 10 volt. R is 1 mega ohm. So 1 times 10 to the power 6. 1 minus e to the power t is 2 microseconds. So we write negative 2 microseconds and tau is 1 microseconds. Now, since this is a ratio of two quantity which have the same unit, the units will cancel. The multipliers over here will cancel. I don't need to write them as 10 to the power negative 6. That gives you I to be equal to 8.65 times 10 to the power negative 6 ampere. Or you can write this as 8.65 microampere. Then in part 3, we need to find what is the time when a long time has passed. So when a long time has passed, that means the current has reached a steady state. And if the current becomes constant, there is no change in magnetic field because of this current. And if there is no change in magnetic field, there is no change in magnetic flux. And without a change in magnetic flux, the inductor does not induces a back EMF. So in absence of any back EMF, the current becomes equal to the same as provided by the battery voltage in the presence of a resistor. The inductor acts as a simple wire without having any effect on the circuit. And you can also check this using the rule. We know that I equals I max 1 minus e to the power negative t over tau. After a long time, we can take the value of t almost approaching infinity. So we get e to the power negative infinity over tau, which is equal to 0. So that gives you I to be equal to I max, which is V over R. V is 10 volt, R is 1 times 10 to the power 6, which is 1 mega ohm. That gives you the maximum current or the current after a long time to be equal to 10 times 10 to the power negative 6 ampere or 10 microampere. Next, let's discuss question 9.50. In the circuit in the figure, R equals 120 ohm, L equals 3 Henry, and V EMF is 40 volt. After the switch is closed, how long will it take for the current in the inductor to reach 300 milliampere? So here in this figure, we have R to be equal to 120 ohm, L is 3 Henry, V EMF is 40 volt, and we need to find how much time it takes for the current to reach I equals 300 milliampere, which is 300 times 10 to the power negative 3 ampere when the switch is closed. So again we use the same rule. Since the switch is closed, the current in the circuit is increasing and we get I to be equal to I max 1 minus e to the power negative t over tau. I max you can write as V over R, which is the maximum current, 1 minus e to the power negative t over tau. Tau is the time constant which we can write as L over R, and t is the time we need to find at which the current will be 300 milliampere. So let's substitute for I, V and R. I is 300 milliampere, so 300 times 10 to the power negative 3. V is 40, R is 120, 1 minus e to the power negative t by tau. Now let's rearrange, move this term to the other side. You get 300 times 10 to the power negative 3 into 120 over 40 equals 1 minus e to the power negative t by tau. So this gives me 0.9 equals 1 minus e to the power negative t by tau. Let's move this to the other side and bring 0.9 here. So you get e to the power negative t by tau equals 1 minus 0.9, or e to the power negative t by tau equals 0.1. Take natural log on both sides. Len e to the power negative t by tau equals len 0.1. When you take natural logarithm of any term, the powers are always multiplied. So negative t by tau len e equals len 0.1. Len e is 1, and to find t, I'm going to multiply with negative tau on both sides. So you get t to be equal to negative tau len 0.1. Tau you can write as L over R, len 0.1. Now substitute L is 3 Henry, R is 120 ohm, len 0.1. That gives you the time to be equal to 0.0576 seconds.